Hello everyone. This is the first meet in the strings meet series. So this meet covers like the basics of strings. So um, and I will cover three topics today. First is string hashing. The second will be tries, and the third will be KMP. So I will start with string hashing. So like
Your voice is cutting in between.
okay, Mhm. I will try to reconnect. Stay. Yeah. So the basic idea of what a string uh, is that it's a sequence of characters. So a character in as we define it in most programming languages would be anything like a letter or a number or any symbol as such. So a is a character, b is a character, and so on, like and even anything like one when you write it like this is a character. uh, Note that characters are like it's a single entity, so something like 12 is not a character. Like this it like 2 and 1 are individually characters, and so on. So dollar sign is a character, and so on. So and string is just a collection of characters. It's like an array of characters. So uh, yeah, so if I put hello each character here, then and this entire thing would be like a string. And strings are generally written in this, it is double quote. So I am using C++ terminology. So um, like you can write strings with a single with single quotes in Python and all, but I'll be using C++ terminology. So this is what a string is basically. And uh, like a lot happens with string. So like and like one of the basic problems we try to solve while thinking about string algorithms is pattern search in a string. So something like, say, hello, how are you? So this is a string, and suppose the pattern I want to find here is uh, how. So in like I want to find how many times and say how at what place this string occurs in the first string. So that would be a classic example of pattern searching in text. So this is a string problem. This is a problem which is solved by string algorithms. And one such and there are several such other problems, like you obviously. So this is one of the basic ones, so which is why I'll be uh, two of my algorithms I will discuss today, which is hashing and KMP. Will try to solve this. And uh, note that these two are not specifically for this. They can be used to do a lot more things, but this is what I will be demonstrating them for today. So yeah, so let us talk about what hashing is now. So hashing is a technique for representing strings as numbers. So wouldn't it be nice, like if I have a string A B C D E, and I could simply represent it using some number, some integer. So note that strings like these are like, the computer doesn't understand what an A is. The computer will only understand that an A is a character. Like it's a sequence of characters where each character is like uh, an ASCII. Like if you know what ASCII is. So uh, each character has a certain number in the certain number to represent it in the in for computers, and like there are other ways to do it, but yeah, so like small a has a value of 97 and so on, and large a has a value of, yeah, 65. So this is the general ASCII representation. And yeah, so the computer doesn't understand what a string like this means. So all it understands is that it's an array with numbers in it. So strings are like a concept in our head, and it's like even arrays are a concept in our, like, I mean, you get my point. Yeah. So what we want to do essentially now is, by using hashing, is like, if I have this string a b c d e, I want to find a technique to map any string to any number, to a number in like in integers. So uh, now another property we want is like, no two strings should map to this integer again. Like I shouldn't have a b c d e and a b c mapping to the same integer. That is not desirable for us. So what we need to define is, now we need to define hash function f, which maps a string, uh, say this, I call this string s, to a number, uh, f of s. So yeah, so f of s will be my hash value. So uh, so yeah, so if so why would we want to do something like this? Simply because, first of all, like, we want to compare, if we want to compare two strings, uh, we could simply compare the hash values. Like, obviously we could simply compare two strings letter by letter, but uh, in some cases, like, having pre-computed hash values for strings might be an easier option for us. So yeah, so this is what hashing tries to achieve. And now let us try to find a hash function. So uh, note that, like, any number we define as, say, 1 2 3 4 5. So if I take a number 1 2 3 4 5 in decimal number system, all it means to me, to the computer, is this: 5 plus 4 into 10 raised to 1, and so on. So like, it's just a, like, this is how I write it, like, right? So like, if this was a string to the computer, this is what it would represent. So why can't we do something like this? So if I have, say, a b c d e, and I just write it as, uh, and I also now define something like an order function. So uh, I say I call this function O. So what O does is, it takes a character, and now it maps it to a number, to a single number. Uh, so O of A would be like, say, we have only A to Z, small a to small z, in our system. O of A would be something like 97. Like, say, I define it to be 0, and so on till O of Z goes to 25. So basically, this just maps our character space to a number space. So this so now, like, we need not worry about actually doing this, because ASCII is already one such mapping. But sometimes you want to avoid extra computation, because uh, say, like, if I am only using A to Z, I need not have all the ASCII values, like I need not start at 97 for A and so on. Like I don't want to waste this. So that's there. So now suppose I already have this order function, like I have an idea of what this is. So what a string would mean to me in such a case would be something like this. So suppose A is my uh, E is 5. So 5 into uh, say we represent it in some base, say P. So this is like base 10, right? So if I have something like P, so 5 into P raised to 0 plus 4 into P raised to 1 and so on till we get to 1 into P raised to 4, right? So we know that this will always give us unique values for a string. Like it's just the property of like the number system. As long as my P is greater than equal to the uh, number of characters I have, like in this case it's 26. So if P is greater than equal to 26, then I am guaranteed to have unique values for a string mapped to a function, uh, s- uh, for this function mapping strings to numbers. So why don't we just use this? Because it gets very big very fast. So like you can see that if P is 26 here, 26 raised to 4 with just 5 characters, I already go very high. And strings are generally large. Like you can have like, so I write a paragraph, it's already like 100 words, and 26 raised to 100 is already way beyond our limits. So why not do something like this? So now we define our hash function, and this is the most commonly used hash function, and be using this uh, we'll be using this for the rest of the rest of the topic. So f of s is sum from I equal to 0 to n minus 1. So s is s0 to n minus 1. It's a n character string. So I goes from 0 to n minus 1. Um, p raised to I um, multiplied by order of si. So and we take a mod m outside. So here we come into the modulo space. So what this does for us essentially is that it reduces our huge space to a smaller space. So we if our modulo is like something somewhere around 10 power 9, we know that our values won't exceed 10 power 9. So this value will never exceed 10 power 9. uh, Now, like, how is this a good hash function? Like, the first thing you will feel is that we can have two strings which are which now map to the same function, to the same um, hash value. So now a few things which we do generally, and which is supposed to be done, and which helps is that P and M are chosen to be primes. So uh, I won't go into the details of why this is helpful, but if like intuitively I can give you the idea that, like, when you take with a prime, you will have much less collisions. So like if I take mod 6, say, then like I am very likely to be left with same remainders, and like, yeah, I won't go into the exact details of this because that is another topic. It's number theory, and even like, yeah, so let's just for now assume that this is a good hash function. I mean, it's not perfect, obviously, but it's good enough like for our needs. So uh like the chances of clashing here are uh, pretty less. So like you will have to sit and find two strings to which actually clash when you choose a decent values of p and m. So in such a case, this is a function we have now that allows us to map a string to a number. So this and this number we will call the hash value. So now let us get to our original problem of uh, pattern matching in strings. So the first thing we will like, how would you do a pattern matching naively? So if I have say A B C D E A B C D E A B C, I don't know. So and we want to find the number of times ABC occurs in this string. In such a case, our naive algorithm would be to do this like start at this point uh, and check whether ABC occurs in this string starting from here. So that would give us we go ABC here, we find it, cool. We increment our count. We start here again, we don't find it, and so on. And we in total we find it three times. So this is a naive algorithm, and say our original text t is of length n, and our string is of length m. What is the complexity of this algorithm? So like I like just put it in the chat if you have an idea. I guess you, most like even the first years have had an okay. Am I actually audible to people? Like I've been speaking for a while now and I don't know.
Yeah, I'll tell you if you're not.
Okay, okay, cool, thanks. Okay, so yeah, so I'll just say it then. So our complexity of this algorithm would be O of mn. And why is that? Like, basically, to do this naive algorithm, what we would do is write a for loop uh, that goes from like 1 to n minus m, and we write another for loop which goes from um, 0, I mean here, like whatever, 0 to m, and basically we start at every I and we check for m spaces after that. So basically we do, and so like checking itself, this is m operations, and we do it n minus m minus 1 times, and this is um, big O of mn. And this means that if our say our text was of length something like 10 power 5, and our um pattern is of length say 10 power 3, in such a case it would require us 10 power 8 operations to actually find the number of times s occurs in t. And you see why this is bad, because we don't want to do this. uh, we want to improve on this. So one one way to do this is hashing. So now we will see like what how hashing helps us. So first I will my screen is also shared. Right? Zoom doesn't tell me it's shared.
Can you please explain how do we find complexity? I really don't.
Okay, so basically the algorithm for the naive algorithm we are employing here is this. So basically, if we have this string, I will just copy it. So if we have this string, so our naive algorithm is something like this. We want to start at every position in the original string. Like we start at position 0 of the original string, and then we go three positions and check for all three characters if they match. So uh, we will try to check if A is same in the first two, B is same in the first two, C is same in the first in the two, and that is true, and hence we increase our count. Like we have a count variable, we just do count plus plus, and now we have found one such thing. However, we have only found it starting from the first position. So now what we do is we shift our original pointer here, and uh, shifting our original pointer, we will uh, uh, now we check for another three times. So we check whether A is equal to B is equal to C, and C is equal to D. All three are false here. So if any one of them is false, then it's obviously not the same string. So we don't do count plus plus, and so on. So basically we move this this uh, uh, iterator. So like this goes through this pointer goes all the way here till here, like till like the third last place, because like whatever. So it goes almost to the end, and in every such iteration, we take around we make three checks. So intuitively, if this was a this was of length n, and this was of length m, so this here n is very large, and m is 3. So you already see how many like comparisons we have to make, right? So in this case, uh, what we do is like our code would look something like this: for I equal to 0 to n minus m minus 1, for j is 0 to m minus 1, uh, if uh, if s of I equal to equal to sorry, I plus j is equal to pattern of j, like something like I will not exactly write out this because uh, uh, like I won't write out the code for the naive algorithm because I have to go on with the hashing part. But the idea is that like you go through the entire first string of length n, and each for each starting point you do m comparisons, and it hence our complexity is approximately big O of mn. So this yeah, so I guess that made it a bit clearer, but I do you like get it more now?
I don't get how the MN is coming. How complexity is direct MN? Do we have to learn that?
So like I think Istasis explained it to you explained the basics of complexity in the previous complexity meet. Uh,
Actually, I was not present in that meet, that's why I don't know.
uh, okay, I
Can you just give a brief note on this? Just a brief one.
Yeah, so there's n elements, and for each element, you can go up to at most m. You're checking it one by one, right? If a character matches, you are increasing your loop by one, advancing your loop. So that loop can go till m operations at most, and there's an element, so that's n times m. For each element, you do m operations at most.
Okay,
Yeah,
thank you.
yeah, that's pretty much the brief of the complexity MN. So I would recommend you to go through the last meet. It should be. Oh, I'm not sure if it's there or not. But yeah, you will encounter this pretty soon. Uh, but I have to move on with the meet for with the main part here. So hashing here now, how do we use hashing to improve upon O of Mn? So notice a very interesting property of our hashing. Uh, if we compute some, so the first thing we would do is this. Uh, if we have yeah, so if we do make a prefix function, so first we now we define a prefix function, say p. No, I'm overusing p. I'll just use something like h. So if we have a function, I have an array h, so where uh, h of I is just is the hash of the string from 0 to I. So um, this is what our basic this is what our each element of the array will look like. So from 0 to I, it's the hash of the string. And this and you see how this is easily computable in O of n time, because if I have h of I minus 1, if I have h of I minus 1, all I need to do is uh, add uh, yeah, p of I into O of Si. So modem. So we have an easy way to compute h of I from h of I minus 1. So in just one loop, I can compute the hash for all the values of this array hash, array h. Now, an interesting property of h of this is if we do h of r minus h of l minus 1. So here r is some position here, and l is a position here. So if we find this value, notice that this is nothing but uh, p raised to l f of uh, s from l to r. Now, where exactly did this come from? Like you can see it from our original formula for our hashing, that like uh, yeah. So uh, if we subtract these two values, all that remains is we can take p of l common, and f, and the rest of it will be the hash of the value in between. So obviously this is modular multiplication, and like everything I describe here is modular arithmetic. So like if you don't know the exact of modular arithmetics, just understand that just like we can do addition, multiplication, division, uh, and like most operations which we do normally are also replicable in the modular arithmetic space. So I think there's a number theory meet this week or next week. they should be touching upon modulo. So don't worry too much about the modulo being there. Just understand that all the operations here are modulo. Like you will figure out what I mean by that pretty soon. So uh, what this essentially means to me is that given this array, I for any substring L to R, I can I can find its hash in one go. So our hash of SL to R will just be h of R minus h of L minus 1 upon P of L. Again, this is modular division. I am just writing it like this just for your convenience. So uh, given this array, we can simply find the hash of any substring pretty easily. Now, what is uh, what's how does this help us? That is mainly that is mainly because first uh, uh, like now we can just rewrite our naive algorithm in a much simpler way. The first thing we do, the first step we take is pre-compute uh, f of our text. So t was our text, sorry, t was our text and s was our pattern. So we can first calculate f of s. So we have this ready from the beginning. This just takes us O of m time. This is length n, this is length m. Uh, so this just gives us our f of s. And second, what we do is we just do the same thing we were doing. We go for I equal to 0 to n minus 1. Sorry, n minus m minus 1. Like yeah, so just take care of the edge cases. And then all we need to do at this point is we can avoid the inner loop completely. So all those m computations we needed all the time now need not be done at all, because what we need is uh, if we can easily find f of s I to I plus m minus 1. Yeah, so this is m characters. So if we find the hash of this pretty easily using this method from our original array, we so this h we compute on the text. So yeah, this should be step 3. Step 2 should be compute h on our string t, and the third step would be this. So we compute the hash value of the m length substring starting from I, and as soon as we have that, we can simply compare it to our f of s. Okay, I am messing up symbols again. I can just uh, keep hearing me, I guess. So we just compare this, and if they match, we do count plus plus. So now you can see that we just have one single loop, and all the operations inside are just are constant time. So that would just mean that we have reduced our complexity from O of mn to O of n. So we this is a pretty big improvement. Like it's really huge. However, the one thing we need to understand here is that hashing is not perfect. So the first assumption we made while defining our hash function this is that f of s1 to f of s2 and f of s2, where if s1 is not equal to s2, f of s1 is not equal to f of s2. This is an assumption we made while defining our hash function. However, like because of this modulo, even though it reduced our output space, it now allows clashing. So we can actually have S1 and S2 which are not equal and give us the same pattern, and thus we could go wrong with this. Now there are ways to improve.
Excuse me.
Yeah.
Could you explain the beginning part of this example again? Till from the beginning till where you've defined the f. Uh,
Mm, okay. Uh, which part exactly? This.
the from the beginning of this, from where you started using hash
Uh,
to, like, not here, like the example
oh,
a
in
little
our
below.
last example.
Yeah, here, from
Okay, so
f. Yeah.
did you get this one?
No, not that either.
Okay, so did you understand how we got the array H? So
No, not really. Like from where you got the array h till function f. There's everything on screen right now. Yeah.
okay. So we have defined a function H, uh, which basically means that which where we have defined an array H where h of I means that h of I is the hash function, hash of the string from the beginning to index I.
Okay.
So so if I am at this uh, f like f of h of 3, that is the fourth element of the array, would mean it's the hash of s0 to s3. So it's four characters, it's the hash of the first four characters. So like now it's easy to see that h of I is computable from h of I minus 1 using this formula. Just using our basic definition of f, we already have h of I minus 1. To get to h of I, we just need to add the hash of the last character.
Yeah.
Uh, okay, yeah, I am going a bit wrong, I think. Yeah. So this adds to the lowest bit. So there is some manipulation you need to do at this part. So um, I will leave you a link to this, and it's much easier to understand it when you read it yourself. But like the idea is that this h can be computed pretty easily in one loop. So that is our main concern here. This h can just be computed in one single iteration through the string, which only takes us O of m time. So now one important property of this h is that uh, we can easily find the uh, no, I was correct about that part. Yeah, it's fine. I'll just keep saying. So h now the difference between the h at two indices is just this prime p raised to l, which is the first, which is like whatever comes before. So here we have assumed r greater than l, uh, greater than equal to l. So everything before that multiplied by the hash of s, the string from l to r. So uh, again, this comes directly from the formula. So it's just like if you imagine it to be something like the geometric series, uh, it's not the geometric series, but like if I subtract these two, all I will be left with is uh, p of uh, if I do h of l r minus h of l minus 1, all I will be left with is p raised to l uh, uh, O of S L and like up to p raised to r and so on. So now if we can take this p of l common, now I will be left with something like this, which again will resemble just the, this is just the hash function, hash of s of l to r. So now that is basically where I get this formula from. You might need to do it, try it out a bit yourself to understand why I get this, but this is the idea of the hash function. So from this array, it's easy to obtain the hash function of anything in the middle. So given two indices uh, L and R, I can find the hash of the string in between. So this uh, allows us to use this algorithm, which is basically
Yeah,
starting
yeah.
at,
I got it from here. I got it from here.
yeah. So
Yeah. Thank you.
uh, yeah, okay. No problem. I'll leave you links to the resources, and it will be much clearer to read it yourself and understand. I will just give the overview here. So now it's pretty easy to see that hashing has improved our performance. However, hashing, as I said, was not perfect, and P and how can we improve our chances of getting things correct by using hashing? The first thing would be like uh, use multiple values of P and M. So if we use P1 M1 and P2 M2 and we define two hash functions F1 and F2, uh, in such a case we can, like, instead of just comparing f, we compare two values, like if f of f1 of this is equals f1 of this, and f2 of this equals f2 of this, only then do I increase the count. In such a case we can see that we have already reduced our chances of clashing, because, like, if it's unlikely in general for two strings to clash using while using a hash function, it is uh, even more unlikely for it to clash when using two. So you can do like three of these or whatever, but I think beyond the point it gets unnecessary. So um this is how hashing helps us, and I have overshot by quite a bit that time. Uh, so yeah, so now I will quickly move on to tries. So uh, a try, whatever we learned earlier is an algorithm. Now we shall define something called a data structure. So try is the first is the uh, most basic string data structure you will encounter, and it is extremely simple. Just that uh, if you are UG1, I guess, then you haven't uh, heard of nodes and pointers, I guess. But like, just understand what I'm saying conceptually, and you don't worry about the specifics of what is happening and how to implement this. That will get clear to you eventually, and you will probably do it pretty fast in your DSA course, and might maybe even in your CPRO course. Uh, Now, what is a trie? So, a problem that trie helps us solve is, suppose we are given a collection of strings. So, uh, say I'm given A, B, C, D, E, F, and another part is another one is, say, A, B, D, E, C, G, whatever, and another is, say, B, E, F, G, whatever, like something like this. Now, suppose I am trying to implement a very basic autocomplete. So now I'm not saying any autocomplete uses this now, but suppose I am trying to build one. So in such a case, say I say this is my dictionary. So I have only three words in my this simple dictionary. Uh, so now what we want to do is we want to find now say our user types A B. We want to find the number of strings in our dictionary which begin with AB. So for now I have reduced our problem from predicting strings to just number of strings, but you will realize that it's pretty easy to just predict strings too. So we want to count the number of strings which start with a given pattern P in our collection of strings. So what would be a very simple way to do this? That would be just go through each string and go through each string in our dictionary and compare number wise and then find which of them actually make sense, which of them actually start with AB and increase our count similarly. So as you can see that it's already pretty bad, so we don't need to uh, like go through everything. So the here is where try will help us. So a try is basically something like a uh, it's like a how do I put it without okay, so it's like a tree. So a tree is a very simple structure. So uh, uh, now say we have nodes. So we have a beginning node which I shall call dollar. So this dollar means that here is where everything starts. So what I will do here is when want to insert a string from the dictionary into a trie, what I do is uh, each of these nodes has a um, map which tells me where to go next. So if I have say two strings in the next part which start with A and B. So if this is what I have in the next thing. So uh, when we want to insert that first word, which is A, B, C, D, E, F, uh, we go into this part. So we go into this part because A is the first letter is A. So again, when we want to have want to go further into the second letter, we go into our next part, which is B. So similarly, A, B, C, D, F. So this is A, B, C, D, E, F. Yeah. So this is what one word inserted into the trie will look like. So it's basically you start with you in each of these uh, nodes you will have only a single letter and a single character and or now what you want to do is um, you want to insert every word in the dictionary into this. So in such a case uh, what what uh, what what happens when we insert the second word here, A, B, D, E, C, G. So note that the first letter for A, B, D, E, C, G is uh, the first letter is A. So I have gone into this path already. I don't need another A because I already have an A. Similarly, as second is also common, B. So the first two nodes for this string, when we insert it, are the same. Now, however, the third one is different. So we need to make another path here. So A, B, D, uh, E, C, G. So this is what a trie looks like. So basically, once we diverge, we never, even though D here is same, we never join back. So this is and again now when we want to insert B, E, F, G, note that we go into this path and not the first letter A path, and this is B, E, F, G. Uh, Now, this is what our trie looks like now, and this is stored in some format, which is which we can easily uh, go through, like traverse in pretty easily using starting from the root. So this node, which is dollar, I called it as the root because it is where everything starts. So now, suppose when we want to search for AB, what do we do? What we want to what we do here is uh, we go in our first path A. Our second also matches with B, and at this point, I just see how many endpoints I have below me. So these endpoints are called leaves. So this is the root, this is the leaves. Uh, I just count how many leaves I have below me. Uh, like I am not exactly giving saying it's always the number of leaves, but basically I'm counting the number of uh, strings I have inserted, which also had this path in common. So note that just by using AB, we already figured out that there are just two strings below me. Now, like it's pretty clear that if this P was of length M, we just needed O of M steps to find the uh, number of number of strings in our dictionary which start with AB. So uh, all we needed to do was like go once into take one step for A, take another step for B, and that's it. So we have already found our answer. So like for those of you wondering how we got to the answer 2 here, so what's a very easy thing to do is like increment the count as we go down. So when we are inserting our first word A, B, C, D, E, F, we do a plus one here, plus one here, plus one here, plus one here, and so on. So uh, and now when we insert A, B, D, E, C, G, we do a plus one here, we do a plus one here, plus one here, we do a plus one here, and so on. So and each of these nodes store values for us. So uh, all we need to do when we search for A, B is get to the final node and count how many plus ones I have done, which gives me the answer 2. So I need to spend nothing more to find the number of things, number of uh, strings in our dictionary which starts with this. So I don't need to worry about right now, since I have defined our problem in this way, we don't need to find which strings these are, but you can see that it's pretty easy to find which strings these are. It's obviously just all the strings which have ended below me. So if I am at this point, I just need to look below me how many strings which are and just collect these. So I just collect A B C D E F and give it as a suggestion to the user. So I just find all the collections, and that is just my basic structure of autocomplete with using a simple try. So like this is what a try looks like. However, like the do you have any questions with this? Like I understand that some of it might be pretty unclear to you, but do you understand the basic uh, concept behind this? Okay, so uh, yeah, so now I will. Uh, I want to do a few more few problems on tries, but that might be a bit too advanced. But so I will cover maybe some problems in the next meet, I guess. Like maybe we could have a strings problem discussion session or something like that. So and also because I'm running out of time for KMP. So now we shall talk about KMP. So KMP is another algorithm. It's called Knuth-Morris-Pratt. So uh, these are the three guys, I think, like found this algorithm, and Knuth is a legend if you want to Google him up. Uh, and like other two are also like anyway. So this is an algorithm which helps us solve our initial problem, which we talked about in hashing. That is finding we have a text and we have a pattern. So we want to find how many times the pattern occurs in this text, also at which places. But that is pretty easy to do once we have how many times. Like I will only explain it for that. Uh, so once now we need to we need to do solve this problem. But now if our text is of length n and pattern is of length m, uh, our KMP algorithm gives us a complexity of O of n plus m to do this. And you might think that this is worse than hashing, but like notice that n plus m is almost the same as O of n. Like it's not very different at all. And it avoids all complications of the hashing. Like you this is like once you do this, you never need to worry about clashing or whatever problems hashing has. So this is a standard algorithm for pattern matching. Like there are better algorithms uh, which do, but the overall complexity remains, even for the better algorithms, it remains almost the same. So also like I will go into a discussion about where and when each pattern matching algorithm is better than the other. But I might do it later. Like there will be several cases like n greater than m and so on. Like in different cases, different algorithms perform better and worse. So KMP is overall a good algorithm. Is all you need to know for now. So notice what we were doing initially. So I was crafting some examples for before, so I will use that. AB, I'll just copy. Uh, okay, so I'll just work with it. Uh, A B A C D A B A B A B C, and what I need to look for is this. So given this is my text, I need to look for the pattern A B A B C. So this is what I need to look for in this text. So manually you can just see that it occurs at one place only. That is, it's here at the end. But this is I think a good example to demonstrate KMP. So uh, I will I will use this now. What we were doing in our naive algorithm when we were talking about starting at each point, starting at each point in our text and doing m comparisons from that point onwards, and then we start again from another point. What we were missing is the inherent patterns within this pattern. So like don't get confused by pattern so much. So but yeah, so A B C. So suppose I have already matched the first two letters. Okay, so no, I have matched the first four letters. So if I have matched A B, but I fail at the next point, so it happens that my next character is uh, something that is not C. So if it's something that is not C, and I have matched till this point, and basically I get stumped at the last position. All I need to do now is like I don't need to restart my search, right? So note that if I have matched AB and AB here, so I can just start comparing from this point to this letter, right? So because I have already matched AB in this text with this here, like this AB here has already occurred here. So this is just like I don't need to do this comparison again, and that is what KMP capitalizes on. So in our ending part of the string, as you will see, it's ABABA. Yeah, so ABABABC. Yeah, so if I match the first four characters of this with this, and when I encounter that sorry, this with this, and when I encounter A which is not C, I don't need to restart my search from B comparing A again and so on. I just need to start comparing this point with this because I have already matched the beginning AB with this AB. So how exactly do we do this? Uh, so now assume now I will introduce you to something called the LPS. Uh, LPS is a array. So LPS is our array here where LPS of I. So what LPS means is longest prefix that is also a suffix. So if you are unfamiliar with the terms prefix and suffix, what they mean is um, A, B, C, D, E, F, G, H, I. ABC is a prefix, GHI is a suffix. So prefix is anything that starts at the beginning of the string and goes on till some point, and suffix is anything that ends at the end of the string. So in such a case, our ABC is a prefix and GHI is a suffix. So there are a lot of suffix. There are n prefixes and n suffixes. And what is a proper prefix? A proper prefix is uh, anything like here. Proper prefix is any prefix that is not the entire word. So essentially I could say that the entire word is a prefix of itself, but that is not a proper prefix, and that's just how we define it. So LPS of I is the uh, is the length of the longest prefix that is also the suffix for the string string s0 to I. So uh, let me just demonstrate this with an example. Uh, if I have A B C D, like whatever. Uh, okay, so I'll just talk about what LPS is first. So give an example for this. Like here you can see that AB is the longest prefix that is also the suffix. So all I want to do is like this is my prefix and this is my suffix, and they are just the longest possible. Like I can't go any bigger because ABA is not present at the suffix. So and also these are proper prefixes and suffixes. So I can't say that the entire string itself is just a prefix and it's a suffix. It's the longest one and so on. So LPS of I is uh, S of 0 to I. So it's the longest prefix that is the suffix, longest prefix, which is also the suffix for the string from 0 to I. So this is just how we define LPS. Now, say we already have LPS. So like uh, with like say some oracle. So you will often hear this term oracle. So say some oracle gives us this LPS. I like they don't, but I will talk about how to compute LPS a bit later. But say I already have, I there's an easy way for me to find this LPS array for for given any string. So if we have this LPS array, uh, if we have an oracle which gives us this LPS array, can you find an algorithm which gives me the number of times uh, this text this pattern pattern S occurs in text T? So like, do you have any ideas how to get the number of times S occurs in T, given a way to calculate this LPS from any string? Like anyone has any ideas, like in case you want to share? Okay, so like a pretty easy way there is to find the number of times S occurs in T would be to just calculate the LPS of S hash T, this string. So basically S plus hash T. So what this means is we concatenate a string. So if I want to look for AB in ABC, I create a new string which is AB hash ABC. Okay, so how does this help us? We calculate the LPS of this string, this new string, And what hash here represents is something which is not in our original character set. So if I am operating within our character set A to Z, small a to Z, and hash is not something which belongs to any of these strings, that is where we use this hash. So AB hash ABC, we just calculate the LPS of this, and that will give us uh, and say yeah. So now give we have this array of this s hash t. All we need to do now is look through uh, everything after the hash. So after the hash, I need to look. So LPS of I, like LPS at any point, would give me the uh, longest prefix that is common with the suffix up to that point. So like I ignore all the values of LPS at these 3 points. I just look here. So here it will give me a value of 1 because A is common with, like, our current string is just AB hash A. So A is common with A, our, and that's the longest. So this will be 1. Now at this point, this will be 2 because AB is common with AB. And for this, it will be 0 because nothing is common. So uh, C does not occur at the beginning, and like you cannot find the longest anything um, which is the suffix and the prefix of this entire string. So all we need to do now is just look through the latter part of the string and count how many times uh, m occurs, the value m occurs in this string. So m, if you remember, is the length of the uh, pattern. So ab, here m is 2. So all we need to do now is look through this string and find how many times 2 occurs. So it's uh, it's clear that 2 occurs only once here, and we already find that AB occurs only once in ABC. So as a more simple example, like more uh, a better example which demonstrates something more. So AB hash AB ABC or something like that. So what will be the LPS values? Just ignore these first three and start from here. This will be 1 2 1 2 1 2 0. So now you can see that 2 occurs 3 times here, which just means that this initial pattern P occurs in our original string only 3 times. So if we break it at this point, AB is the prefix and the suffix. AB here also, AB is the prefix and the suffix. AB is the prefix and the suffix. So AB has occurred 3 times in our original string. So this is a pretty easy way to find the number of times, and also you can find where exactly it occurs. So it's not a big deal to find exactly where in the original string this occurs. You just need to do a bit of calculation and subtraction here and there. So you just need to subtract n m and this one, and yeah, you'll just get it. So at this 2 position, I just need to subtract these 3, and then I just need to give this position as our starting point of the string where of the pattern. So uh, given the LPS, it is pretty clear how to find our original, how to find the number of times the pattern occurs in the text. However, I haven't told you how to calculate the LPS. So I have just told you that.
Hello, sir.
Yeah, yeah. Good.
Sir, if we take A, B, A, sir, instead of A, B, then
Okay.
how will it calculate?
Uh, okay. So A, B, A, and do you want to talk about what will be the LPS array for this, or do you want to talk about how it will match?
How we can match?
Okay, so if I use the same string here, A, B, uh, B, A, B, C. I'll just write it out a bit bigger. C. Yeah, so now I just ignore these values. I start here. Here I know that the longest prefix that is common with our suffix is A itself. So it's just length 1. Again, we move one more, and we see that LPS array should give me a value of 2 here. And if we move again, we will see that this entire suffix and prefix are common. So the longest prefix that is also the suffix will be 3 here. So I am not talking about how LPS array gives us these values, but uh, given that we get the LPS correctly, these are what the values should be. So again we move here, and here notice that for AB, uh, AB is the longest prefix that is also the suffix, because anything more than that does not satisfy it. So note that BAB could not be the a prefix, or ABAB could not be a prefix because I have a hash here. So our value here will be 2. Again, 3, 2, 0. This is how our LPS will look, and see how many times 3 occurs here. It's once and twice. So is that correct? Yeah, it's correct, because ABA occurs twice in this text. So is this clear?
It's clear, sir.
Okay. So now, like, if our LPS given our LPS, we it's pretty easy for us to find the number of times this happens. So however, the challenge here is to find the LPS, and the algorithm for calculating LPS is just O of n. So given a string of length n, our LPS is calculated in just O of n. And like, you can see why I was saying KMP can find it in O of m plus n, because I just have n characters here, one character here, n characters here. So my LPS is just calculated in O of m plus n plus 1, which is just O of m plus n. So this is uh, this is how KMP does pattern matching given our LPS. So how exactly do we calculate the LPS now? So this is a bit of a challenge, uh, and this algorithm is not easy. So once you understand it, it's easy, but it's not easy to come up with on your own. And secondly, even when you understand it once, uh, it's not easy to remember how it exactly works. Like, even before this meet, I had to look it up once again, and that will probably happen with you every time. But it's very interesting. It's very interesting, and if you enjoy algorithms, you will probably enjoy this algorithm. So this uh, LPS is also called the prefix array. I think it's called the prefix array. Yes. So this prefix array finding algorithm is uh, this. So can you see VS Code now? Like,
No.
No, we can't.
okay, so I think I need to share my entire screen for that. Uh, oh, I can share my VS Code. Oh, I'll just share my entire screen.
We can see it now.
Yeah, I'll just need to switch back and forth. So I'll just share this. So this is GFG code. Uh, don't judge me for it, but like I this is correct. So which and it's properly commented, which is why I'm trying to explain using this. So yeah. So KMP will be divided now. Like I will just be talking about this part. So just the compute LPS array function. I'm just talking about this. So the rest of the algorithm, GFG has used a different algorithm. Like it's not the S plus hash plus T algorithm. It's a bit different, but it's the same thing. It's the same complexity. You can read it up if you want to, but I use the CP algorithms one because it's more intuitive for me. So compute LPS array basically uh, what it does is first I start with LPS 0 equal to 0. So I know that from for the first um, okay, so for the first letter in a string, so if I have this string A, B, C, D, E, F, whatever, I should probably use a better string. Yeah, I'll just use this. So we can see that for our first number, for our first character in a string, the LPS value should always be 0. Why is that? Because we are not allowed to have proper suffixes, right? So we know that the longest proper suffix, which is also the prefix, is 0 here. And now we start a loop from our value 1, that is this point. And what we do now is this: we initialize I uh, we initialize len, which they call here len, to be 0. Like we are our len is this upper arrow to be len here, and I is we start from here. Now what we do is we go till the end of the loop, obviously. And what we do simply now is this: if our uh, if our current if our current LPS, so len represents for me here the length of the longest suffix, that is the prefix till the previous point. So if I have my string to be till this point, like if I have uh, um, I minus 1 characters already evaluated, and I just want to talk about the ith one, I know that the LPS of this string could could be just the 1 plus the LPS of this and this entire string. To demonstrate it, what I mean is like if I have AB, sorry, yeah, so if I have AB and uh, my I already my point len is here, so my len is 1 because I have already calculated our LPS for this initial prefix, so that is just 1 because A is common. Now I know that if I want to add a new character, like find the LPS for this point. So we want to find the LPS 3. In such a case, if this character matches this character, that is LPS of previous one plus one matches our current character, we just have AB common. I'm cluttering it up too much, but yeah. So if A is common here and both of the next characters are same, then I just have I my length of LPS for this point increases by one. So this is all that is being done here. So if pattern I is equal to pattern len, then I just increase my len, that is my and I assign LPS of I to be len, and I increment my I. That is, I just move on and assign this to be 2. So I had already assigned this to be 1. My len was 1, and since this and this matched, I can just now set a len to be 2 and assign this to be 2 and move on to the next point. So this case is clear. Uh, and now the second part. What if they don't match? In case they don't match at all, like, so if I had something like this, A B A D, and I have already evaluated LPS till this point. Now my what will be my value of len? Len will be 1 again. My len pointer will be something somewhere here. My j will be here. I mean, sorry, len will be here and j will be here. Now I see that B and D don't match, right? So if my B and D don't match, and my now what would be a trivial case? So sorry, uh, if my B and D don't match and my len was already 0, so that would be some case like this, A B C D, where I have evaluated ABC till this point, and my L, len here till when I have my pointer here, my len will be 0 because my LPS of this string is just 0. So if that is the case, then I know that I cannot do much more, and my yeah. So that is this case. So if length is 0, like our LPS of the string till before that is 0, in such a case, I will do LPS of I 0 and I plus plus. So I will just uh, I will just go on to the next character, and before doing that, I will just assign this LPS to also be 0. Just because that my current character does not match with this, so A does not match with D, and I cannot find anything better. So I just assign LPS 0 for D, which once you see carefully, it's correct. Now this is the tricky case, and uh, this line is difficult to understand why, but I will try to explain it here. And this is the toughest part of uh, KMP itself, but you will need to try out a few examples yourself to get it. So but I will go through this. So ABAD. So if we have this, and we have evaluated till ABA, at this point I am my J my I is here and my len is here. My len is equal to 1. So I am here. B and D do not match, and len is not 0, which means I had something common before. In such a case, what I want to do is I need to set my len to be uh, LPS of len minus 1, I think. Yeah, yeah, len minus 1. So basically, I am setting my len to be, in this case, I am setting it to be uh, LPS of 0, which is LPS of this was 0 itself. So I set my len to be 0, but this is a trivial case, and I will explain this better on a better case. Uh, so okay, P, yeah. So this should do it. Uh, now, if I want to calculate my prefix array at this point, so now notice here, uh, I am here. My I pointer is at here, which is I think 6. Yeah, so my I is 6, and what will be the value of len here? Len will just be the LPS of the previous string, that is 3. So my len equal to 3 will be here. So I like ABA equals ABA here. So I guess that makes len equal to 3 makes sense to you. So now what I do is this. My A and D do not match, and my len is not equal to 0. Uh, in such a case, what I want to do is set my len to be uh, LPS of len minus 1, which is LPS of uh, 2. Now, I why is this uh, why do we do this? Because notice that ABA might be the longest prefix, that is the suffix, but it's not the only one. You can see that A is also candidate, which is the prefix and the suffix. So we cannot really move on with saying that the LPS of this value should be 0 without really evaluating whether whether AB whether this is true or not. So say this was B, then I cannot really say LPS of this point, LPS of I will be 0 without actually checking whether AB and AB match. So yeah, so what we do here is uh, notice the LPS of our original array would be something like 0, 0, 1, 1, 2, 3, right? Yeah, so and LPS of 2 here would mean 1. So basically, my len goes from here to here, which means that I have just reduced my it's in a sense I compromised my longest wala part. So I compromised my longest wala part, and I took a smaller prefix, that is the suffix a, and now I can again do the comparison part. So notice that I have not increment I here, which makes sense because I can now again compare B with B, and I will see that this matches, and I will be left with this case, which would give us 2 here. So this is the essence of the LPS calculating algorithm, and I don't know if I think who asked me the proof of the algorithm, whether of this running in O of n time. So notice that our I is not incremented here, but so if you want, if you could wonder that whether I will keep hitting this case all the time. But notice that this will not happen because when we increase len, it increases by a step of one, and when we decrease LPS, it also always decreases. So it does not. It does not. It's not. It never stays the same, which means that our even when we do this, we will only do it a finite number of times as compared to m. So uh, I am not exactly going into the details of that here. So uh, you can see on a macro scale that this runs with in a complex with a complexity of O of n, where n is the length of the string. Don't get confused by their m. So this is what LPS calculating algorithm looks like. I know it. This last part specifically is heavy, and even I don't remember it, as you could see, because it's not really intuitive, this line specifically. But yes, if you have any questions, doubts, whatever, you can ask me now. And I need to wet my mouth. I'm
I had a question regarding the hashing part, right?
okay. Go on.
So when you were searching for it,
Hmm.
so when we computed hi, at some point it would overflow the modulo, right?
Yeah, that no, it will never overflow the modulo
No, I
because
meant as in it will wrap around or whatever, right? Like
it will.
so, one that uh, effect would stored in hi. How can we guarantee that when we're searching for it, one that modulo mess up the calculations when we're searching for another string?
Actually, what I say here as h of r minus h of l minus. So note that when we do a modulo, our if we do a modulo m, so if we do mod m, our final value, whatever is here, will always be in the range of 0 to m minus 1. And of course, I am not talking about the C++ modulo here. I am talking about the mathematical modulo, like mod. There are subtle differences, and it's good if you could Google that up. With negative numbers and all, it messes up. So just be careful with that. However, your point is very valid because I am not guaranteed to have h of r greater than h of l minus 1. Like
Yeah,
is that what you
yeah,
mean?
yeah,
Yeah,
yeah.
yeah. So even this subtraction is modular. So what I mean by that is this minus this mod m, and that again gives us a positive number. So so like my minus 2 mod 3 is 1. So that is how it's handled. So uh, I I'm using this symbol very frequently, but note that it's mod maths wala mod, not C++
Okay.
wala mod.
And one more thing. So in
Hmm.
tries, you showed it as like a bunch of nodes leading to each other, right?
Yeah, yeah, yeah.
So at each node, suppose from the root, I want to go to A,
Hmm.
and I want to make sure that there is no string like AD.
Hmm.
I'd have to allocate space for that also, right? Is there a way I can dynamically make sure that I'm only allocating space for characters I want?
Yeah, that is exactly what we do. As in, if I have no AD, I will never have this branch. So uh, there will not exist this branch at all. So this is done using struct in C++, uh, and pointers. So
But you'd still need a pointer to each element to say that this place doesn't exist, right?
yeah,
Or
so
do you?
basically what happens is inside each of these node is a struct, and inside each of the struct you can have an array. Say I call that array as a map. Like it's not the same map. Like I'm just calling this array as map. Here map of I will give me -1 if that does not exist, or it will give me the pointer. Like it'll give me a null pointer if it does not exist, or it gives me the pointer to D if it exists. So this is how it's handled.
But for
Hmm.
each node, it would be 26 pointers, right? Or maybe
Yeah.
52. So
That will be true.
can you? Is it possible to make sure that I'm only allocating for a node, like for a letter node, not the entire set, to save in space? Can we implement something like that?
What I talked about here is an array as a map, right? So there exists C++ STL ka map, which does exactly what you are talking about. So it does not store map of D at all. Like unless I insert a value into it, it does not store anything. That increases our handling time, as in, so if I want to look for map of, if I want to look for the pointer which points to D, it will take me some more time than an array would take because it's constant. However, it saves me space.
How does it do that?
So map itself, C++STL, like you should look up what STL map does. So std map. Uh,
Okay.
so it's yeah, I'm not going into details of that, but this is the answer to your question. So you should probably look that up. Hmm. Any more questions by anyone else? It's pretty impressive. 19 of you stuck around till the end. I thought I would have zero participants by the end. Okay, so I will probably discuss a few, like the prefix function I talked about. The LPS itself uh, is a very powerful thing, and it's not just for string matching. It can be used to solve too many interesting questions, and I will probably talk about it in the next meet. But like it will not be basic. So there's that. Okay, yeah.
If if you when you're talking about hash functions, is
Hmm.
it possible to like generate a perfect hash for a particular set? Like how would you do that? Like if you wanted to make sure you'd have no collisions
Like like it's practically not possible to have zero collisions because
for some data set, like if you know that you're going to run it on only a particular set
yeah,
of strings.
the first thing is, if you know, if you're going to run it for like 10 words, why don't you create a hash function that uh, maps these strings directly to some number? So there's always that. So if you have a limited data set, you can just hand code or just find simple values for that. However, like in general, it's not possible because pigeonhole principle. Because like if I do mod 10 power 9, like if my if I have to, C++ has to store it within 10 power 18, right? So however, there like at some point i- it's bound, if my mod is 10 power 9, 10 power 9 plus 1 strings would always make something clash. So uh yeah, I mean it's and you can see that the number of strings is way more than that, uh, because of the length and whatever permutations.
Okay,
So
suppose I
uh,
had like more than what I could hand code and less than 10 power 18, so say like on the order of like 10 power 4 or something like that. Is it somehow like possible to generate like a perfect hash somehow? Like is there some
uh,
algorithm for that? Or?
Yeah, so there is something called SHA-256 if you have heard of it. It's a
Security thing?
yeah, it's a hash function, and I think that is the best hash we have. I am not confident about what I'm saying beyond this point. So I think that is the best hash function we have, and it's near perfect. Like it probably doesn't like you have to sit and really find what clashes to actually make it clash. So there are pretty good hash functions, much better than this. But for most of our purposes in CP, we don't need to go into that good stuff.
Okay, thank you.
Okay. Uh, Thank you everyone for attending. Now I'll stop the recording and end the meet. Thanks a lot.